I want to look at four consequences of the mean value theorem. The first two are consequences which make it so that textbooks put it towards the beginning of chapter 4, and the last two are ones where some textbooks put it at the end of chapter 4. And I like it at the end, which is the way I'm presenting it here. So here's the first consequence. It says if f prime of x is bigger than 0 for all x on the interval from a to b, then f of x is increasing on a to b. And what does increasing mean? Increasing means if you've got two x values, x1 and x2, where x2 is bigger than x1, then the function value at x2 will be bigger than the function value at x1. If this is always the case, that bigger x values give you bigger y values, then we say it's an increasing function. So here's my quick proof of this, or at least some justification as to why. So take two values of x somewhere between a and b, okay, where x1 is less than x2. Okay. And we're going to see if we can show that f of x2 has to be bigger than f of x1. So notice that to say that the derivative is positive everywhere, you're saying the derivative exists, so it's a differentiable function. If it's differentiable, it's got to be continuous. So the mean value theorem applies here. And so there exists a c on the interval from x1 to x2 where f prime of c equals f of x2 minus f of x1 all over x2 minus x1. Well, let's multiply both sides by that denominator. Whoops, I got stuff down here. So I've got x2 minus x1 times f of x, sorry, f prime of c equals f of x2 minus f of x1. And notice this thing right here is bigger than 0. This thing right here is bigger than 0. Right? This one's bigger than 0 because x2 is bigger than x1. This was the hypothesis. Both of these things are bigger than 0. So I've got this thing right here, f of x2 minus f of x1 is equal to that, which is bigger than 0. So this thing is bigger than 0. So f of x2 is bigger than f of x1. So the bigger x value has to give me the bigger y value because I got positive slopes everywhere in between. Okay. Likewise, next consequence. If f prime of x is 0 for all x on the interval from a to b, then f of x is decreasing on a to b. What does decreasing mean? Well, decreasing means that if you take bigger x values, they'll give you smaller y values. Okay. The proof is almost identical to that. The only difference being is that at this point, right, if I had this hypothesis, then this would be negative. This would still be positive times the negative would be negative. So this difference would be negative, so this would be turn that inequality around, and so that would turn this inequality around, and we'd have to say that the bigger x value gives us the smaller y value. Okay, so when you're drawing graphs, this is what we were using, saying, hey, I know if the derivative is positive, this thing's going uphill, and if the derivative is negative, the graph's going downhill. You know, I think you could probably figure that out without knowing the mean value theorem. But you know, now you know for sure. Okay, so there's the first two consequences. The third one is kind of in between those two, and it's important enough to rate its own name. It's the zero derivative theorem. It says if f prime of x equals 0 for all x on the interval from a to b, then f of x is a constant function on that interval. Again, not too surprising, but again, take a look. I'm not going to give a formal proof here, but it's the same idea that if you take any two x values, x1 and x2, and take a look at f of x2 minus f of x1 over x2 minus x1, right? This has to equal f prime of c for some c in between x2 and x1, okay, by the mean value theorem. Well, if this right here is always equal to 0, then you've got this fraction equal to 0, which means the numerator is equal to 0. So f of x2 minus f of x1 equals 0, which tells me that they're equal to each other, that f of x2 equals f of x1. So if that's true for every pair of x's that you choose, that they always have the same function value, then this must be a constant function, right? The graph of the function looks something like that. Derivative 0 everywhere. It's a constant. This is our first step into integral calculus, into our Calc 2, where all through this course we've been taking a function and taking its derivative and then doing stuff with the derivative. Now we're saying, hey, I know the derivative. What can you tell me about the function? So this is going backwards, right? So if I tell you that the derivative is equal to 0, you can tell me, well, that function is constant function. Don't know which constant, but still, it's a constant, right? That's the first step into Calc 2, right there. And then the next step is what's called, let's see if I've got it down here. Yes, I have what's called the constant difference theorem. And it says this: if you've got two functions that have the same derivative, if f prime of x equals g prime of x, for all x on the interval from a to b, then the difference between the two functions is constant. Right? And this is fairly easy to prove. Actually, let me point out there, the first, when I'm doing this live, I asked my class, hey, suppose you got two functions of the same derivative. What can you tell me about the functions? There are people that want to say, well, they must be the same function. And then someone will say, well, no, consider something like x squared, right? And x squared plus 2, the derivative is 2x here, the derivative is 2x there. So they're not the same function, but all you did was add a constant on. Well, that's what this is saying, is that to say that the difference between them is constant is the same as saying that f would be equal to g plus a constant. Okay, and to see that this is the case, you look at the function h of x equals f of x minus g of x. Right? H prime of x is f prime of x minus g prime of x. But I'm told that the f prime and g prime are the same, so this is equal to 0. So h is a function where the derivative is always equal to 0. So by what we just did up here, right, by the zero derivative theorem, h must be a constant. So h of x equals a constant, but h of x was equal to f minus g, so f of x minus g of x equals a constant. Or, if you'd rather, f of x equals g of x plus a constant. This is, either way, the constant difference theorem, sort of, you want to put the answer this way, but the way we use it quite often is to say that, hey, if I've got two functions that have the same derivative, then one of them is just the other plus a constant. Okay, constant derivative theorem. Those are the consequences of the mean value theorem that we use. The first two to help us draw graphs, the second two to step us into Calc 2.